Welcome to the second part of this webinar series on securing IoT applications with Mbed TLS. My name is Tschofenig, I work at Arm and help to make Internet of Things more secure with my contributions to standards. We covered bridge yet secret key based Ciphersuites in the first part of the webinar, and they came with a number of great benefits. But there are also drawbacks. Sharing a key may not be suitable in all environments. In 1976, public key cryptography was invented and allows the private key to be kept secret while the public key is shared. In this webinar, we will explore how TLS works with Ciphersuites that use public key cryptography in combination with certificates. When we talk about TLS with certificate-based authentication, then we obviously have to create certificates first. We want to use mutual authentication between the IoT device running the TLS client and the TLS server. This implies that both the TLS client and the TLS server need to be provisioned with certificates. This is different to the web PKI model, where certificates are mostly used by web servers only. In fact, it would be a mistake to apply the web PKI model to the IoT environment since the communication patterns are very different. There are many different PKI deployments, and we use one with a single CA that signs both client and server certificates, as shown in this figure. For this purpose, we have to create a CA certificate that serves as a trust anchor. The CA certificate is self-signed. Then we use the CA key to create the client and the server certificate, which are illustrated below here. And the client will have to store the client certificate plus the corresponding private key and the CA certificate. The server will have to store the server certificate plus the corresponding private key. It will also have to authenticate the client, and for that purpose it will most likely have to store the CA certificate. In some deployments you have to reuse an already existing PKI, and hence the example has to be adjusted slightly. If you want to learn more about the PKI, I can recommend a book by Russ Housley and Tim Bolk with the Best Practices Guide for Deploying Public Key Infrastructure. The next few slides explain how to use OpenSSL tools to generate public-private key pairs and certificates. I will not go through them in detail, but the command line options shown here are sufficiently counterintuitive to have them written down for future use. When you execute these commands, you will be prompted to enter some information. Since we matched the common name in the certificate against the server name, it matters what you enter. If you use the server name indication as an I extension, you can set the server name and also the common name to any value, but if you don't, then the name in the DNS needs to match the content of the common name. Otherwise, the handshake will fail. First, we need to create the CA certificate. This is relatively easy since we only need a self-signed certificate for it. We use elliptic curve cryptography here with a NIST B256R1 curve. The first command lists the available curves available on our system, and the NIST B256 curve should be among them. The second command generates the key pair and stores the private key in the ca.key file. The last command then produces the self-signed certificate and stores it in ca.crt. Generating the server certificate is slightly more complex. After we generate and store the private key in server.key, we have to create a certificate signing request, CSR, which we store in server.csr. You can also print this certificate signing request. Then we need the CA to produce the server certificate, which we store in. The process for creating the client certificate follows the description of the server certificate. The resulting files are client.key for the private key and client.crt for the client certificate. So here's the private key and here is the certificate. There are two unfortunate side effects of using certificates. A certificate contains an expiry date, and this expiry date needs to be checked. In order to do so, an IoT device needs to understand the notion of time. It falls outside the scope of the TLS protocol how this time information is obtained. Furthermore, checking whether a certificate is revoked is also necessary, and various ways exist. A popular approach is to use OCSP stapling, an extension to TLS, that conveys status information about certificates in-band in the TLS handshake. It's also worthwhile to mention that certificates and trust anchors may need to get replaced during the lifetime of a device. However, these topics are not covered in this webinar. Let us start with the description of the TLS protocol. Two popular public key crypto systems emerged over time, namely RSA and elliptic curve cryptography. We focus on elliptic curve cryptography, or ECC, since it is the preferred crypto system for IoT devices due to the smaller key size. As a reminder, I will show the key length slide from last time. We will use a Ciphersuite that is recommended by RFC 7925, which is called TLS-ECDHE-ECDSA with AES 128 CCM8. This sounds pretty complex, but it's just an algorithm that uses an ephemeral elliptic curve Diffie-Hellman exchange, ECDHE, and the elliptic curve digital signature algorithm, ECDSA. ECDSA, like the original digital signature algorithm, has the property that poor randomness used during the signature generation can compromise the long-term signing key. For this reason, the deterministic variant of it, documented in RFC 6979, is implemented in Mbed TLS, which uses the private key as a source of entropy to seed the random number generator. If you want to learn more about how elliptic curve cryptography works, I've included two resources here, one talk and one book. If you look at the red box, then you will see that elliptic curve cryptography uses much shorter key size than RSE-based crypto systems with the same strengths. A shorter key size here means much less data to exchange. Hence, elliptic curve cryptography is preferred for IoT security. To put the use of certificate-based authentication in the context of the TLS protocol, let us look again at the two-phase design of TLS. Regardless of whether you use pre-shared secrets, as we did in the first webinar, or certificate-based authentication, the record protocol will always use symmetric key cryptography. In fact, we use even the same cipher, namely AES 128 CCM8, in both webinars for the protection of application data, which in our case is HTTP. The use of certificate-based authentication really concerns the handshaking protocol, as shown in those boxes. Let us look at the handshake in a little bit more detail. In part 1, we also looked at the handshake, but omitted a few messages which weren't relevant for BSK-based authentication. This time, we have to consider the full handshake, since that's what we need for certificate-based authentication. There are a few new messages you haven't seen before, namely the certificate messages, the certificate request message, as well as the certificate verify message. The server key exchange and the client key exchange message already showed up last time when we talked about the BSK Ciphersuite. However, the content of those two messages depends on the selected Ciphersuite and will be different with the Ciphersuite we look at today. We get to this very soon. The certificate request message, as the name indicates, is used by the server to request the client to send a certificate, as well as to effectively perform mutual authentication. The certificate message is the container carry a certificate or a chain of certificates, since we may be sending more than one certificate in this message. The certificate message, however, does not exchange or convey the trust anchors, which may come as a surprise to some. Trust anchors have to be pre-installed on the client and also on the server. The certificate message is used by the client here to demonstrate possession of the private key when performing client-side authentication. All other messages have been explained already in part 1 of the webinar. So let's have a closer look at how the ECDHE-ECDSA exchange looks like. Here are the detailed ECDSA exchange, which we have chosen to use with our Ciphersuite. In a nutshell, the Diffie-Hellman exchange is used to derive keys by both parties. ECDSA is used for authenticating the parties. It's important to note that there are two key pairs present on the client and on the server side, namely the ephemeral elliptic curve Diffie-Hellman key pairs, but also the long-term keys, which we created at the beginning of the webinar. On a high level, the steps are as follows. The server generates an ephemeral elliptic curve Diffie-Hellman key pair and places the public key in the server key exchange message. It then signs this message with the long-term private key. In step 2, the client also generates an ephemeral elliptic curve Diffie-Hellman key pair, places the public key in the client key exchange message. It uses the certificate verify to demonstrate possession of the long-term private key and sends the certificate verify and also the client key exchange message to the server. In step number 3, both parties use the elliptic curve Diffie-Hellman algorithm to derive symmetric keys and to use those indirectly for the master secret calculation. The master secret is what is used to produce the keys needed for the record layer, and in our case for use with AES 128 CCM8. With this background knowledge about the TLS exchange, let us do the hands-on. We are again using the same test setup as in part 1 of the webinar. The hardware platform is a Keil evaluation board which uses an Arm Cortex-M4 MCU, and we use the Ulink Pro debugger. Furthermore, we make use of the Keil RTX5 as an operating system with the Mbed TLS and the networking middleware. The demo setup is also unchanged. The client is connected to the server via switch. The server side runs the SSL_server2 example program provided with the Mbed TLS source code, which you can obtain from the GitHub repository. We again use the C preprocessor directives to guide our build process for Mbed TLS. We focus on the use of elliptic curve cryptography as previously explained, and use the recommendations from RFC 7925. The config.h settings for the TLS-ECDHE-ECDSA Ciphersuite with AES 128 CCM8 are more complex and require some explanation. First, we only focus on TLS 1.2, which is why we only compile that code. Then we include the key exchange for ECDHE and ECDSA. We reuse the same settings for AES, CCM and char 256 as we had in our first webinar. But this time we need to include all the support that is needed to get elliptic curve cryptography working, which includes the ECDH functionality, ECDSA signature algorithm, the elliptic curve implementation, and also a big num library for multi-precision integer library. Additionally, since we use certificates, we need to have support for the ASM1 library and certificate parsing, and we also want to indicate the NIST curve B256R1 that we want to make use of. The SNI extension allows the client to tell the server what entity it wants to talk to. This is particularly useful in a hosting environment where multiple domains are run on a single server with a single IP address. It's also useful in our test setup where we don't actually make use of the DNS. Finally, we enabled the NIST optimizations and decided to use the deterministic ECDSA, which is documented in RC 6979. Let us have a look at the application code sequence. It still has the same steps, but there are some additional configuration steps to consider. The client application has to pass various certificates, including the CA certificate, the client certificate, as well as the private key. This is done in step 1 when we initialize the session data. Next, we initialize the random number generator. We establish a TCP connection. We then configure the TLS stack, and thereby we also need to load the CA certificate we previously passed, as well as the client certificate and the private key. We configure the SNI parameter and also the curve. Then we are ready to run the TLS Handshake protocol in step 5. We will at the end of the handshake verify the server certificate. Finally, we are ready to exchange application data, and in our example code, we then immediately tear down the communication and free the state. Here's the command we run on the server side. we use the SSL_server2 example and indicate where to find the previously generated server certificate and the server private key. We also indicate that we want to use mutual authentication, which will trigger the server to issue a certificate request message. Here are these relevant configuration parameters. Also mode _required demands mutual authentication. Here we include the server certificate with CRT_file and also the server private key with key_file. And finally, we also provide a pointer to the CA certificate, since the server receives the client certificate and needs to also validate it. With my example application open in Microvision 5, we can now have a look at the code. Let us start with the config.h file. And I explained already previously most of the settings, but I would like to just point out one thing, namely the elliptic curve cryptography support requires a lot of additional functionality and a lot of additional code, which you can easily see when you look at this configuration file setting. I talked already about TLS 1.2, about the key exchange that we have to enable, also about the curve that we are using. But then we have to include the ECDH library, the ECDSA code, multi-precision integer library, as well as the elliptic curve code itself. We already had the code for AES CCM SHA-256 previously included, but this time we also need to include support for all the certificate-related parsing, ASM1 libraries, the X509 extensions, and so on. We had the NIST optimizations enabled, the ECDSA deterministic support, and also the server name indication, which you can find here. I've also used some additional parameters for the NIST optimizations, which are listed here. Essentially, we are enabling all software optimizations, and there's no hardware crypto acceleration support available on this board. Also worthwhile to point out is here I enabled the middleware, the Mbed TLS middleware with version 2.6.1, and of course I have already configured the networking stack. I'm not going to show how to configure the networking stack here. So let's have a look at the application code, at least at the most interesting parts. We had already seen the configuration of the server name and the server board previously, so we need to indicate on which server we want to talk to. Here you just had an IP address pre-configured in my example. Of course, this could also be an FQDN. What is interesting here is the SNI setting, so I have included the server.example.com as an SNI setting, which is also what I had configured for my server certificate. So those two match, so we'll be fine. And I want to use a specific Ciphersuite, namely this one, the one that we talked about throughout the webinar. If we look a little bit further into the code, you will see that there are the certificates, the CA certificate, the client certificate, as well as the private key of the client here is included in here, in this case in BEM format, just that included it here, basically copied it in here from the files that we previously created. If we go a little bit further, you see these extensions for initializing data. We create the structures for the CA cert, for the client cert, and also for the private key. And then we also have to pass them here. So there's a separate Mbed TLS API call for passing the certificate, which we are doing here. We do the same not only for the CA certificate, but also for the client certificate. And we also pass, of course, the private key itself. Once that parsing is done, we establish a TCP connection as previously explained, and then we need to do some additional configuration on the TLS stack itself. So when we come to the configuration, you see that I'm configuring the stack to use the CA cert as well as the client certificate as well as the client private key. I configure the curve, which obviously we didn't have to do when we talked about the pre-SK based Ciphersuite. And then we are good to go. We can run the handshake, and subsequently we can verify, once the handshake is completed, verify what we got as the server certificate. And in our case, we actually print the content, so we will see it in the debug window. And then finally, we exchange the application data, the request and response, and we'll be done with it. So let's have a look. I compiled the code already. Let's compile it again and load it to the board. And then let's start the debugging. So we shorten this step. We don't step through the entire code, but we go straight to the part that is relevant where we actually see the result of the exchange. So let's go to the place where we write the first GET request. Okay, in this window below, you can see the debug output. So we went through the different steps. You may have noticed that it took a little bit longer. So the public key crypto for the full exchange is recognizable. And we see here with the information printed about the server provided certificate after the successful TLS handshake that we have successfully authenticated the server, and he placed in the common name field the server.example.com identifier in there, which we had expected. So you also see that this is signed with ECDSA, hashed with SHA-256. As we indicated during the certificate creation, this is a 256-bit ECC cert. Then if we want to go all the way to the end of the exchange, let's continue. So you see we have successfully completed the exchange. We negotiated the TLS handshake with the Ciphersuite that we had previously been indicating in the code. And then we see a couple of error messages. Those are just to let us know that the peer notified us that the connection is going to be closed, which is what the server code does. Once it successfully provides a response back, it immediately closes the connection. It's not what we would typically do with an IoT application, but in this example application, that's exactly what we want. So this concludes the hands-on session, and you will be able to get the code and have a look at it yourself, and feel free to modify it accordingly. While public key cryptography has many benefits, there is also a price to pay. Let us have a quick look at the performance of the resulting exchange. Here's an example of the message size of a complete TLS handshake with the discussed Ciphersuite. As you can see, it is much larger than the BSK variant discussed at the first webinar. Changing certificates as well as the ECDHE public keys is recognizable. The red boxes are supposed to illustrate this. Certificate message from the server, certificate message from the client. The key exchange messages, as explained earlier, contain the Diffie-Hellman public keys, and in this case for the server key exchange, also the signature of it, which is separate for the client key exchange. This chart shows the performance of the elliptic curve digital signature generation on 4 different development boards using several NIST curves. In this legend you see the NIST curves with a different key length, and also those are the different boards being used here. And in this performance measurement, NIST performance optimization has been enabled. So with full performance optimizations, but no hardware accelerations. There are 2 observations you would be able to make very quickly. First, public key crypto is more performance demanding than symmetric key cryptography. By now I believe you understand why we want to use this 2-phase approach with TLS, where symmetric keys are used for securing application data. The speed of the processor matters, and so does the key size. The 32 MHz Cortex-M3 is much slower than the other tested MCU. As you can see here, this is the L152RE with running at 32 MHz. This chart shows the performance of different operations on the LPC1768 board with different optimization levels. Creating a digital signature is faster than a corresponding verify operation. ECDHE is roughly as expensive as the ECDSA verify. Enabling optimizations makes a lot of sense, but it costs a lot more RAM. So using 50% more RAM increases the performance by a factor of roughly 8 in our performance measurement. And the performance data has been collected for a NIST lightweight crypto workshop in 2015. To estimate the performance of the full handshake, the ECDSA sign and verify, as well as the performance of the ECDHE numbers, have to be added up, since all 3 operations are used in handshake. Additionally, certificate verification has to be added to get to the total number of the milliseconds that have to be spent on with cryptographic operations. Having looked at the performance of the full exchange, it is reasonable to discuss optimizations. I will focus on a few selected extensions, but they are more described in RFC 7925. The most widely used optimization used with TLS is session resumption, which is already specified in the base TLS RFCs. The idea of session resumption is simple. Instead of executing a full handshake, an early exchange is just continued by utilizing session data stored on both sides. This session state is indexed by a session ID. In a full exchange, the server allocates a new session ID and will provide it in the server hello. First, the client starts with a client hello with an empty session ID. Later, when the server processes the client hello and decides to establish session resumption functionality, it provides and allocates a session ID in the server hello. Then the regular handshake is concluded. When the client wants to resume an existing session, it then includes this session ID from the full exchange in the client hello. The result is that the exchange is shortened and the changed cipher spec and finished messages are exchanged immediately afterwards. So the handshake is abbreviated. As we can see here, the server hello is followed immediately by the changed cipher spec and the finished message, and the client does the same without having to exchange any further messages, even though the full exchange required the use of public key cryptography. The benefits are clear. Few messages are exchanged, less bandwidth is consumed, and the computational overhead is minimal since only symmetric key cryptography is used. Due to the handshake property, a server can delete stored state at any time and reject the session resumption attempt by the client, and thereby force the client to enter a full exchange. Session resumption without server-side state was introduced as an extension to the classical session resumption mechanism. It is specified in RFC 5077 and is also known as the ticket extension. As the name indicates, it provides the session resumption feature previously described, but without having to store state at the server side. The server thereby encapsulates state information in a ticket, which is protected against modifications, and stores it at the client. This extension is negotiated in the client and server hello. When supported by the server, a new message, the new session ticketed message, is used to convey the ticket to the client. The client again starts to indicate support for this extension in the client hello with an empty session ticket. Then the server hello, when it supports this extension and also wants to use it, it returns the session ticket message, also empty, and later includes this new session ticket message in the exchange. This figure illustrates the case where the client presents the session ticket in a client hello, which is then used by the server to resume the previously stored state. It also issues a new session ticket for a subsequent exchange. Here we see the ticket added by the client to the client hello. The server indicates that it supports this extension and resumes the session, issues a new session ticket message, but then goes on with the abbreviated handshake. The benefits are similar to the session resumption mechanism, but there is also increased scalability due to the distributed session storage on the client side. This extension is very popular as a performance enhancing on the web, but also for network access authentication using the extensible authentication protocol in enterprise Wi-Fi networks. The TLS cached info extension is yet another extension specified in RFC 7924, which aims to reduce the amount of data exchange between a client and a server. It uses the basic observation that some information in the TLS exchange is fairly static, such as certificates and the list of certification authorities. In an environment where clients frequently talk to the same server or servers, which is definitely the case in most IoT deployments, the server certificate does not need to be exchanged when the client had previously cached it. The client informs the server about information it has cached with this new extension, and then the server would only include a fingerprint of the certificate or the certificate chain rather than the certificate or the chain itself. In this table, the certificate provided by the server as well as the certificate request can be omitted or better replaced with a fingerprint of that exchange using the TLS cached info extension. For also avoiding the transmission of client certificates, another extensions may be used, namely the certificate URI extension specified in RFC 6066. It allows the client to point the server to its certificate rather than conveying it within the handshake. This is the client certificate that could be omitted or replaced by URI instead, thereby reducing the over-the-wire transmission overhead. There are further extensions that impact performance, which are worthwhile to mention. The raw public key extension uses raw public keys instead of certificates. This mechanism combines low overhead with the benefits of public key cryptography. The maximum fragment length extension provides a way for the client to tell the server that it has limited RAM available for incoming messages, thereby allowing to reduce RAM usage needed for the TLS exchange. This is specified in RFC 6066. The trusted CA indication extension gives hints to the server what trust anchors the client has provisioned. This helps the server in selecting certificates presented to the client, since in many IoT scenarios the client will typically have a very small number of trust anchors only, so selecting the appropriate certificate is important. Finally, it's worth noting that TLS code can be reused at different layers in the protocol stack. For example, Wi-Fi authentication often uses TLS-based protocols for authentication, and the same is true for mesh networks such as Thread. Additionally, it's even possible to reuse the TLS-DTLS handshake at higher layers, as it is currently discussed in the IETF. As a summary, there are various TLS extensions available that help to improve the performance of the exchange, mitigating some of the drawbacks of public key cryptography. With this background knowledge about the session resumption, let us do another hands-on session. The config.h settings for session resumptions are simple. No additions are needed for plain session resumption since it is a feature of the base TLS RFCs. To enable session resumption without server-side state, as defined in RFC 5077, it is necessary to add the Mbed TLS _SSL session tickets preprocessor directives. The Mbed TLS client application needs to change a bit when using session resumption, as this slide illustrates. Our code needs to do 2 or more TLS handshakes. The initial exchange performs the full TLS handshake and establishes the state or the ticket. Subsequent exchanges utilize the established state to perform session resumption. First, we need to initialize the session state and configure the TLS stack to use RFC 5077 style session resumption. This is shown here, and also later on the configuration of session resumption without server-side state. If we don't use that feature, then nothing changes in step 4. There will be some trigger, such as an error situation, where we are forced to rerun the handshake. So in our case, step 7 is where we encounter an error. The initial handshake gets closed and then we re-establish another one. When this happens, we use the stored session state and enable it for use with a subsequent handshake. And this is the second branch, step 8 to 12. Of course, we have no guarantee that the server will utilize session resumption, since the server could fall back to the full handshake. In our example, the server performs session resumption, then we continue exchanging application data. In the end, we tear down the communication free state, including the session resumption state. In step 8, we set the session state, which is then reused in step 10 when we initiate the TLS handshake again, but in this case, due to the established session state, we can do the session resumption. We'll see that in the code in a minute. I have started now a Keil MicroVision 5 with this new enhanced application program, which uses the plain session ticket mechanism, the session resumption mechanism. And I've also enabled started Wireshark and I'm trying to capture all traffic through the board that I'm using, which is 4433. So we can actually see some messages flying by. Therefore, I had to configure the switch that it uses board mirroring, so I actually see the traffic flowing between the development board and the server. Okay, so let's get this started. So in the example program, what you're going to see is first we are running through the full handshake, and I set a breakpoint at the stage where before we send the HTTP request, and then later on we see session resumption following afterwards. Okay, let's get started. It takes a little bit of time to run through the main handshake as we have seen before. So we see the successful authentication. We are now ready to save the session, as it can be seen here. So Mbed TLS _SSL _get session is used to store the session state. We skip over that. And now we are ready to send a request, as it is shown here. Let us do that. We send a request and we subsequently wait for the response. So now everything was like before. We did the full handshake, we protected the application communication, and now we are ready to close the session, and we have already received the close notification from the server side. So let's have a look at the Wireshark. So we see the usual TLS communication, client hello, server hello, and so on. So if we look at the client hello, what we will see is, first of all, we see that the session ID hasn't been set yet. The server side will respond with a session ID set. This is the session ID in this field, so 32 bytes. And then we see the regular handshake proceeding till we exchange application data and tear down the communication. Good so far. So let's continue. We are now getting to the phase where we are re-establishing the session based on the established state. So let's continue. We ran through another session resumption phase. So as we see here, performing the TLS session resumption, it was extremely quick. We barely even noticed it, thanks to the abbreviated handshake. And now we are ready to send another request. So let's send the second request and we get the reply back. Let us switch back to Wireshark to see what the outcome of this was. We see, first of all, the client hello message now. It contains the session ID we've seen previously. The server hello, in this case, doesn't matter. But what the exchange clearly shows, immediately following afterwards is the changed cipher spec, and then the encrypted handshake message is the first finished message provided by the server, and then the exchange is finalized and the application data is protected. So this was the abbreviated handshake. So let's expand this scenario a little bit when we use or enable a session resumption without server-side state. So I define here to enable it, and of course I also had to include the C processor directive Mbed TLS _SSL session tickets. I compiled this in already, and now when I set this value to 1 in my configuration, I actually enable the use of that extension in the code. So if we have a look at it, go through the current project, we can see during the configuration of the TLS stack, we use the Mbed TLS _SSL _conf session tickets to configure the use of session tickets. So let's do that as well. We stop the entire exchange again and stop Wireshark. Okay, I'm ready to go. Let's compile the code So the code with the RFC 5077 session resumption is now on the board, and let's get it started. So what we are now going to see is that the initial exchange, the client hello and the server hello exchange, will have an indication of the ticket extension, and then we'll also see the new message, the new session ticket message being used as well. That's the difference to the previous exchange. Okay, let's do the initial exchange, the full handshake which establishes the ticket. Takes again a little while. We look at it again. We see the client hello, and here we see the extension that is being presented here by the client, the session ticket extension based on what we configured in the stack, and the server response with the session ticket extension in the server hello. Also, it has an empty length just to indicate that the server supports it, but the actual ticket will be sent much later in the exchange. And here's the new session ticket message. And in this case, our session ticket has 484 bytes and encrypts the entire state information. Okay, good so far. We store the state, the ticket, and start sending the first request, and we get a response back, and the server finishes the exchange. And now we are going to resume the session and use our ticket that we have just obtained. Let's do that. As before, it's extremely fast, but we successfully did the TLS session resumption, in this case without server-side state. And then let us finish this exchange. We again send the get to the server and wait for the response. We are done. So let's have a look again. The exchange continues. Now in the client hello of the session resumption case, we now see the session ticket message, which is not like previously empty, but now it contains the session ticket. It's the ticket we have just gotten before, just injected here, and the server hello confirms the use of it. And we see the exchange immediately following the changed cipher spec, followed by the finished message, which is the encrypted handshake message here, protecting the application data subsequently, and then finalizing the exchange again. So we tear down the exchange. Here we get another session ticket, which I mentioned earlier. Every time we go through an exchange, the server provides a new session ticket, or it can provide one if it wants to do so. So now we have completed the exchange. And so the changes that are needed from an application side of view, not a lot between the plain session resumption and the session resumption without server-side state. Let us conclude this webinar with a short summary. BSK-based Ciphersuites offer great performance. Certificate-based Ciphersuites offer an alternative where the private key is not shared, which gives a security benefit. Public key crypto is, however, more demanding for performance. This performance impact can partially be mitigated using TLS features, such as session resumption and TLS cached info. Which Ciphersuite to use depends on your needs and your threat analysis. I would like to thank you for your attention.